Hello, today we're continuing in our series on nuclear physics, looking at the extreme single particle model. As ever, I shall take a simple approach, dipping in and out of quantum mechanics. It gets the right answer, but it's more of a hand-waving argument. But hopefully it will be easy to follow and enable you to access the more complex and correct route. Well, we said when we did the semi-empirical mass formula that there was a term at the end which was to do with pairing. And you may recall that the argument was that if you had two nucleons, that's two protons or two neutrons, they would form a bond between the two, a pair if you like, that would have a strength, that bond. You would have to put energy in to break it, and consequently that was the equivalent of deepening the binding energy. So if this is the potential well, which represents the binding energy, what the pairing does is essentially to deepen or strengthen that binding energy. Well, if that is true, then that means to say that if you've got an even nucleus with an even number of protons and an even number of neutrons, all of them are capable of forming pairs. And if they do, then they will attain that additional binding energy. And the way they attain that additional binding energy is to align themselves so that the total angular momentum of each pair is equal to 0. And they also ensure that the total magnetic moment of each pair is 0. So they simply align themselves so that the spin of one nucleon is in the opposite direction of the spin of the other, and that gives you the lowest energy level, and that of course is what nature seeks. But suppose you've got an even-odd nucleus. Now it doesn't really matter whether it's the protons that are the odd number or the neutrons that are the odd number, but either protons have got an even number and neutrons are odd, or it's the other way round. Now everybody can form a pair in that scenario except one nucleon, which is, as it were, on its lonesome ownsome. And consequently what the extreme single particle model says is that the entire nuclear characteristic will be determined by that one outstanding nucleon, because all the rest will pair to give an angular momentum of 0 and a magnetic moment of 0. So to the extent that the nucleus has an angular momentum and a magnetic moment, it will be wholly due to that one outstanding unpaired nucleon. Now, from the video we did on nuclear spin, we showed that the total magnetic moment, whether it be for the spin or angular momentum, was equal to a constant which we call G, multiplied by the nuclear magneton over h bar times the value of S or L, as the case may be, where the nuclear magneton is equal to E, the charge on the electron or the charge on the proton, times 2h bar divided by 2 times the mass of a proton. And from that we might reasonably conclude that the total magnetic moment would be equal to the combination of the spin and the angular orbit terms. So it will be this G term, which is the L version of the G value, times Lz plus G for the spin times Sz, all multiplied by the nuclear magneton divided by h bar. That's simply taking this formula and saying that the total magnetic moment is the combination of the angular momentum and the spin, where the GL and GS represent the constants associated with angular momentum and spin respectively, and Lz and Sz are the values you measure. Remember, when you actually do an experimental measurement, you measure along an axis. We always traditionally say, conventionally, that we measure along the z-axis, or some of you would prefer me to say the z-axis. And we've already established what these values are, whether it's for a proton or for a neutron. We've got that the GL value for a proton is 1 and for a neutron is 0, and the GS value for a proton is 5.5857 and for a neutron is minus 3.8260. Why does a neutron have a magnetic moment for spin when it has no charge? It's because it has within it 3 quarks, each of which are charged. So when you spin, you get an effective magnetic moment because you've got 3 charged particles that are spinning. Now we just remind ourselves that the total angular momentum is equal to the orbital angular momentum plus the spin angular momentum. And spin angular momentum only has 2 values, plus or minus a half. Strictly plus or minus half h bar. So J is just going to be L, the angular momentum quantum number, plus or minus a half. And we remember that ML, that is the magnetic, magnetic quantum number, has values of L all the way from minus L up to 0 up to L. And they are in whole numbers, of course. So let's first of all think of this when J is L plus a half. We'll do L minus a half in a little while, but for the time being we're looking at J equals L plus a half. And the options we've got are minus L through to 0 to L, and for S we've got plus half or minus a half. And what I want to know is what combinations of these values and these values give me L plus a half. And there is only one combination, when this value is L and when this value is plus a half. No other combination will do. For example, you can't take L minus a half and add a value from here to get L plus a half. So only when this term is L and this term is plus half do you get L plus a half. Now we are going to be performing an experiment to measure the magnetic moment of the particular nucleus we want to consider. When you measure a magnetic moment, you do not, of course, ever measure the magnetic moment of a single nucleus. You actually measure the magnetic moment of billions of them, and you get an average. And the way we write the average magnetic moment is in angle brackets. That is sometimes called the expectation value, though it is not necessarily the same as the expected value. A better term is the average value. And that is going to be equal to, just to say what we said before, GL times LH bar plus GS times plus or minus H bar over 2, but in this case it's plus a half because we said the values were plus L and plus a half. And that will all be multiplied by the nuclear magneton divided by H bar. Remember, although we said before just L and S, that was a shorthand of recognising that actually each of these values are multiplied by H bar, so that you've got, in this case, a whole number multiplied by H bar, in this case either plus or minus a half times H bar, but we are using J is L plus a half, so it's L and a half H bar. And you'll notice from this that the H bars actually cancel, so this just becomes GL times L plus GS over 2, all multiplied by the nuclear magneton. And that's going to be equal to the average magnetic moment that we measure when we do the experiment. So it really was as simple as that. And we know the values of GL and GS for protons and neutrons. For a proton, the average magnetic moment is going to be GL, which is 1 times L, so it's just going to be L, plus GS, which is 5.5857, divided by 2 is going to give you 2.7928 times the nuclear magneton. And that's for a proton. On the other hand, if you want to look at a neutron, then the average magnetic moment is going to be equal to, well, it's going to be GL, well, GL is 0, so that term just goes to 0, plus GS over 2, well, GS for a neutron is minus 3.826, so if you divide that by 2, you get minus 1.913 times the nuclear magneton. That's for a neutron, and you'll notice that there is no L dependence in that at all. So just to recap, this is the general formula for the magnetic moment of a nucleus when you have J in the L+1/2 state, and these are the specific answers for protons and neutrons separately. But it might not be L+1/2. We've also now got to consider the J equals L-1/2 state. And how can you get L-1/2? Again, you've got the options of minus L up to 0 up to plus L, and for spin you've got a half and minus half. What combinations of those two will give you this? Well, obviously one combination is L and minus a half. L and minus a half give you L-1/2. But there's another option, and that's L-1, which is obviously between 0 and L, and plus a half. Both of those combinations will give you a total of L-1/2. So this is where we dip into quantum mechanics a bit, and we say that essentially the total wave function of the two options here is equal to some probability amplitude times psi1, where psi1 is the L and the -1/2 state, plus some probability amplitude times psi2, where psi2 is the L-1 and the +1/2 state. And if you're wondering about probability amplitudes, you can find out more by looking at that series I did on quantum mechanics. It was the first one of the series of, I think, 6 that I did last year that explains what probability amplitudes are. But to save you looking it up, for the purposes of what we need to know is that if you square probability amplitudes, you get the probability of getting each of these in turn. So let's start initially with the L and the -1/2 option. So we're looking at the L and the -1/2 option, and we go back to our formula that the magnetic moment, or the average magnetic moment, is going to be equal to GL LH bar plus GS H bar over 2 times mu n over H bar, and the H bars cancel. But now we just have to remember that our values for L are L and our values for S are -1/2, so strictly this should be minus GS over 2 because we are using values of L and -1/2. Whereas if you look at the L-1 +1/2 state, then the average magnetic moment is going to be GL times now L-1. I can leave the H bars out because they're always going to cancel. And now plus GS over 2 because we're using the +1/2 state, and all of that will be multiplied by the nuclear magneton. So these are the two formula. This is the one for when it's L and -1/2, and this is the one for when it's L-1 +1/2, and both of them, of course, contribute to the L-1/2 state. And we want to find the values of A and B so we know what probabilities there are of each of these arising. And what we're going to do is we're going to use the ladder operator, or sometimes called the raising operator. And if you don't know what that is, you might want to look back at a video I did called Particle Physics 1, and at the time 50 minutes and 16 seconds, you will find that I write something that looks a bit peculiar. It looks like this. And just very briefly, what that means is that A plus is what's called a ladder operator or raising operator. And all it means is that if you use that operator, quantum mechanical operator, on a state n, it will give you the next state up. But for normalization purposes, you have to multiply by the square root of the value of that state. So if we're talking about energy levels, and you've got a particle in that particular energy level, what we're saying is that the mathematical representation of this is that if you apply an A plus to that level, call that level n, what that essentially does is the equivalent of raising the energy level to the next level. But you have to put this, sorry, that shouldn't be a plus, that should be an equal sign. So A plus acting on n equals n plus 1, so A plus raises the state from n to n plus 1, but it has a normalization factor in front of it. Well, I'm just going to use, instead of A plus, I'm going to use J plus, which is the angular momentum raising operator, and that is equal to a combination of L plus S plus. So L plus, I think reasonably self-evidently, is the operator that raises state L to L plus 1, and the S operator will raise state S from minus a half to plus a half. Now, in fact, you can't go from L to L plus 1 because the maximum value is L. The options are minus L through to 0, through to L, in units of 1, whole units, integer units. So actually you can't go from L to L plus 1, that would not be allowed. But you could go from L minus 1 to L, that would be allowed. So what happens when either of these operators operate on a state that is already at its maximum? The answer is you get 0 return, because obviously once you're at the maximum, these operators cannot take you up any further, and so you get 0. So what I'm now going to do is to apply J plus to each of these terms here, this term and this term, and essentially I'm using this as a proxy for psi1, my wave function, and I'm using this as a proxy for psi2, my wave function. Remember, psi2 was associated with L and minus a half, and psi2 was associated with L minus 1 and plus a half. So if I apply J plus to this term, and then I apply J plus to this term, we'll see what happens. So let's do first of all this term here. So what I'm going to do is to do J plus acting on GLL minus GS over 2. Right, that is essentially my wave function, or at least what I call my proxy for my wave function. It'll do for these purposes. And that of course is just going to be equal to L plus into GLL minus GS over 2 plus S plus into GLL minus GS over 2. In other words, J plus is just the combination, the linear combination of the orbital angular momentum raising operator plus the spin angular momentum operator. And you'll remember the rules, 2 important rules here. Firstly, the L operator only acts on L, it doesn't touch S, and the S operator only acts on S, it doesn't touch L. And if you're already at the maximum, then the operator must return a value of 0 because you can't go beyond the maximum. So it's pretty clear what's going to happen here. L plus will act on L, it doesn't act on S, but L is already at its maximum, so this term is 0. Then we've got S plus acting on L, well, it doesn't touch L, so it leaves that alone, and then it takes this minus half term and raises it. So the answer here will be GLL, because that term is untouched, plus GS over 2, because you've gone from a minus half state to a plus half state by virtue of the raising operator. But remember, we needed this square root term of n plus 1. That's the square root of this value. What was this value? It's plus a half. So we need in front of this term the square root of a half as our normalization factor. So since we've got a times psi1 here, and we're using this as the proxy for psi 1, what essentially we could say is that J plus times A of GLL minus GS over 2, which is the proxy for psi 1, is equal to, well, it's just this term times A. A times the square root of 1 over 2 times GLL plus GS over 2. And now we're going to apply J plus to the second of the two terms, which is my proxy for psi 2. So I'm going to apply J plus to GL, and you remember it was L minus 1, plus GS over 2, and that was my proxy for psi 2. And of course that's going to be equal to L plus of GL L minus 1 plus GS over 2 plus S plus of GL L minus 1 plus GS over 2. So now we take L plus, which is a raising operator, and act it on the state L minus 1. L minus 1 will of course raise to L, so we're going to get GL times L plus GS over 2 because L plus doesn't touch the S side of the business. And then over here we've got S plus acting on L minus 1, which it doesn't touch, plus GS over 2, which is the plus half state. That's already at its maximum, so LS plus acting on the plus S state, a plus half state, gives you nothing. So this side of the equation is going to be nothing. But of course we're going to need, as usual, the normalization factor, which is the square root of the state that you get to. So this is going to be the square root of L, because that is the final state. So it's the square root of the value of the final state, which is the normalization factor. Which means that J plus on B of this value here, GL L minus 1 plus GS over 2, is going to equal B times what we get here, the square root of L, into GL L plus GS over 2. So if we go back to that formula which I devised just a little while ago, that the total wave function is the probability amplitude A times psi 1, which is the L and minus half option, plus B times psi 2, which is the L minus a half plus half option, and then apply J plus to all of that. J plus on psi is J plus A psi 1 plus J plus B psi 2. Push that up a little bit. Then what we've got to do is just simply say that J plus acting on psi is equal to J plus A psi 1, which we calculated. You remember that was A times the square root of a half into GL L H bar plus GS. Actually, I don't need the H bars, do I? We cancelled those out. Plus GH plus GS, GS over 2. Plus, and then it was B, the square root of L, into, let's hope I can get this, GL L plus GS over 2. That was this here. And now comes the clever bit. What we're going to do is we're doing an experiment. We are actually going to, as it were, measure psi, but we measure psi at its maximum value. In other words, we're aligning it, let's say, with a magnetic field. So that we can say that when we apply J plus to a maximum value, that will give us 0. So the whole of this term here is equal to 0. Now you'll notice that GLL plus GS over 2 are common factors, and so those, since it equals 0, you can cancel those out. And that gives you that A times the square root of 1 over 2 plus B times the square root of L equals 0. If we square, or sorry, take this over the other side, you've got a times the square root of 2 equals minus b times the square root of L. And now you can square both sides. That'll give you a squared over 2 is equal to b squared L, which means that a squared is equal to 2b squared L. But you'll remember that I said that a and b were probability amplitudes and their square represents probabilities. Now what we're saying is that psi is, let's go back up, psi is a times psi 1 plus b times psi 2, and that's all there is, which means that the probabilities must add up to 1. So a squared, which is the probability, plus b squared, which is the probability, equals 1. So that's another term that we can write. A squared plus b squared equals 1, which means that b squared equals 1 minus a squared. So you can feed this into this formula here. You get a squared here is equal to 2l into 1 minus a squared. And that means that a squared equals 2l minus 2la squared. Take this on the other side, you now get a squared into 1 plus 2l equals 2l. And that means that a squared is equal to 2l over, well, put it the other way around, 2l plus 1, which is the same as 1 plus 2l. And since from this formula a squared is 2b squared times l, or 2l times b squared, that means that b squared must equal 1 over 2l plus 1, because a squared is 2l times b squared. Well, if this is b squared, multiply it by 2l, you get a squared. So now we've got a squared and b squared in terms of the orbital angular momentum number L. So just to recap, we are looking here at the J equals L minus a half state. And we said that that could be occasioned by having L and a minus a half. And it could also be occasioned by L minus 1 and plus a half. And then we calculated the probabilities, well, not the probability amplitudes, we looked at the probabilities because we looked at a squareds for each of those. So that means that the total magnetic moment, or the total average magnetic moment, which of course will be the combination of these two types of state, will be equal to a squared, which is the probability of getting the psi 1 state, which we said was GL L minus GS over 2, and then plus b squared into the psi 2 state. So b squared is the probability of getting the psi 2 state, and the psi 2 state we said was GL L minus 1 plus GS over 2. And all of this, of course, has to be multiplied by the nuclear magneton. So that's going to be equal to, well, a squared we now know is 2l over 2l plus 1 into this term, plus b squared, which we now know is 1 over 2l plus 1 into this term, and the whole jolly lot, of course, is multiplied by the nuclear magneton, the whole term. Well, what I can obviously do is to take out the 2l plus 1 and put that over here as well. So those cancel. And now if I multiply through 2l times in brackets here plus 1 times what's in brackets here, I'm going to get 2l times GLL is going to give me 2GLL squared. And then 2l times minus GS over 2 is going to give me 2LGS over 2, which is minus GSL. And then here I'm going to get plus 1 into GLL, so that's plus GLL. Then I'm going to get 1 into GL times minus 1, which is minus GL. And then here I'm going to get 1 times gs over 2, so that's plus gs over 2. And all of that, remember, is multiplied by the nuclear magneton divided by 2L plus 1. And now what I'm going to do is to separate out the GL and the GS parts. So I'm going to have GL into, well, here I've got 2L squared. I've got a GL term here which is plus L, and I've got a GL term here which is minus 1. And then I've got GS terms. Well, here I've got minus L, and here I've got plus a half. All multiplied by the nuclear magneton over 2L plus 1. Now I'm going to recall that we are looking specifically at the J equals L minus a half term. We did the J equals L plus a half earlier. That was a doddle. This is turning out to be quite complicated. J is L minus a half, which means that L is J plus a half. So I'm going to make this even more complicated by substituting that L is J plus a half. And let's see what we get. That's going to be equal to, this is GL into 2L squared, but L is J plus a half. So first of all, we need to know what J plus a half squared is. Well, that's J squared plus J plus a quarter. But this is 2 of those. So that's going to be 2J squared plus 2J plus a half. J plus half squared is J squared plus J plus a quarter. Double it, you get 2J squared plus 2J plus a half. So that's that term. And then L is just, of course, J plus a half. So that's plus J plus a half. Actually, I don't need that bracket there. Minus 1. That's the GL term. And then I'll put it down here, plus GS into minus L, which of course is going to be minus J minus a half, plus a half. Right, well, here you've got minus a half plus a half, so those go. Here you've got a half plus a half minus 1, so those go. And you've got 2J plus J, so that is going to be equal to GL into 2J squared plus 2J plus J is plus 3J, and then plus GS times minus J is minus GSJ, all multiplied by the nuclear magneton divided by 2L plus 1. Well, now we're going to convert L into J. So 2L is 2J plus 1. 2J plus 1 plus 1 is 2 into J plus 1. And I can simplify that a little bit further by simply dividing through by J and putting the J here. So that's going to be GL into 2J plus 3 minus GS, all multiplied by the nuclear magneton times J over 2J plus 1, because what I did was to divide through by J and put the J here instead. And that, I remind you, is the average magnetic moment measured if you are talking about the J is the L minus 1/2 state. So that's the general term for the L minus 1/2 state. And if we are talking about a proton, let's move this up. So if we're talking about a proton, then the average magnetic moment is going to be GL, which of course is just going to be 1. So that's going to be 2J plus 3. That's minus GS. Well, for a proton, that's 5.5857 times, of course, the nuclear magneton J over 2J plus 1. That's always there. But plus 3 minus 5.5857 can be simplified, so that's just going to be 2J minus 2.5857, all multiplied by the nuclear magneton and J over 2J plus 1. Which I can simplify still further by simply dividing through by 2, so those 2's cancel there and divide that by 2. I get J minus 1.5857 0.2928 mu n J over J plus 1. And that is the average magnetic moment for a proton. And if it's a neutron, got this term again, for a neutron GL is 0. So all you're going to get is minus the GS value. And for a neutron, the value is minus 3.826. So you're going to get a minus, which means that for a neutron, the average magnetic moment is just going to be plus 3.826 multiplied by the nuclear magneton times J over 2J plus 1. Or again, that can be simplified still further to say that the average value of the magnetic moment is going to be just divide by 2. That's going to give you 1.913 times the nuclear magneton times J over J plus 1. And that's for a neutron in the J equals L minus a half state. So let me remind you what we have calculated. We said that the value of J is L plus S, but S can either be a plus half or minus a half, which means there are two options. J is L plus a half or J is L minus a half. We started by looking at J is L plus a half, and we calculated that the general form of the magnetic moment was given by this, but that if you substituted in the values that we know for GL and GS for a proton, you get that the magnetic moment is J minus 2.2928 times the nuclear magneton, and for the neutron, the magnetic moment is minus 1.913 times the nuclear magneton. Looking back, I see that when I calculated this, I did it in terms of L, but of course L is simply J minus a half. So if you substitute in for L J minus a half, then you get this term here. And then it took us longer to do the J equals L minus a half, because there are two ways that contribute to this. You can have values of plus L and S is minus a half, or you can have values of L minus 1 and S is plus a half. They both contribute to L minus a half. So we had to do all those probabilities, but we got a general formula like this. And then for a proton, the average magnetic moment will be J minus 1.2928 times the nuclear magneton times J over J plus 1. And for the neutron, the average magnetic moment will be 1.913 times the nuclear magneton times J over J plus 1. So let's just calculate what that means for this is the magnetic moment, and then J will have values of a half, 3 halves, 5 halves, 7 halves, 9 halves, and so on. That's the J value. J is, remember, L plus or minus a half. So let's think first of all where you have got J is L plus a half. Well, when J is L plus a half, we can do the neutron term very easily. It's not J dependent. It's minus 1.9 throughout. So for a neutron, if this is minus 1.9, let's call that there, the values for each of these, you shouldn't draw a straight line, of course, because they are discrete values. The J values can only ever be half, 3 halves, 5 halves, and so on. Whereas if you look at for a proton, you've got J minus 2.29. Well, let's start with J as a half. When J is a half, 0.5, that means that this magnetic moment is going to be about minus 1.7. So it's going to be slightly higher than this value. When it's 3 halves, you're going to get 1.5 minus this, which is about minus 0.7, which is about here. And then it's actually going to go up. The next one will be plus 0.3. It always goes up, of course, in units of 1. So it's going to look something like that. So that essentially, if you were to join it, you get a straight line. this is a straight flat line, and this is the neutron value, and these are the proton value for J plus a half. Now you can see that when you're looking at J minus a half, the calculations are going to be a little bit more complicated, but what they will actually derive for you is something of the order of lines that look a bit like this, but of course there'll be individual points rather than lines. They're called Schmidt values. And those are the theoretical predictions of the magnetic moment based on the formulae which we derived at great length. And what you find when you measure the magnetic moment is that it sits somewhere in the middle of all these points. And what conclusion you draw from that is a very simple one, that the extreme single particle model, which takes as its thesis that the characteristic of the nucleus is wholly determined by the one remaining odd nucleon, because all the others are paired, and paired such that their total angular momentum comes to 0, and that therefore the only angular momentum that matters is the angular momentum of the odd remaining nucleon. What we can conclude is that can't be right, because experimentally we don't get those values. We get broadly along those lines, but there must be more to it. And it's the what's more to it that is going to sort us out something further in terms of the nuclear model.